In this video, we are going to cover a slightly different method that can be used for finding the volume of a solid of revolution. We're going to talk about what's known as the shell method. So we're still dealing with solids of revolution. So imagine you have some area in the xy plane, and you're taking this area and you're rotating it around an axis to create a three-dimensional solid of revolution. In the previous video, we learned that if we slice our solid perpendicular to our axis of rotation, our cross sections are going to be discs or washers, so circles, or maybe circles with holes in them. Well, it turns out we can actually compute the volume by slicing our object parallel to our axis of rotation. So in my example that I have drawn on the screen, my axis of rotation is a vertical line. And if I want to make my little rectangles or my slices vertically, if you take one of these little rectangles, which is parallel to the axis of rotation, and you rotate it, what you're actually going to get is a cylindrical shell. So the object you're going to get is a cylindrical shell. Visualize perhaps maybe a roll of toilet paper, where you can imagine you have a bunch of cylinders kind of stacked up on top of each other. And so the cylindrical shell, or the cylinder we get, has some height and a radius. And how I have it drawn in this picture, the width of my cylindrical shell is a little dx, or delta x. Now, if I want to find the volume of this cylindrical shell, so cylinder with a hole in it basically, the way to do that is imagine that you take a scissors, you cut one edge and you roll it out flat. Imagine you have maybe a can of soup and you're taking the label off of it and you roll that flat. You are going to get a rectangle. And the height of the rectangle is going to match the height of the cylinder. The width of the rectangle is going to be the circumference of our cylinder. If you pull that cylinder apart, it's going to give you that rectangle, and that width is the circumference of the circular part of our cylinder, which can be found using the formula 2 pi r. So what that means is the area, the surface area, or we could say lateral surface area of our cylinder. So the area of the sides of our cylinder is going to be 2 pi r times h. 2 pi r times h. Now, this is technically a cylindrical shell. It's got a little width, which is a dx or a delta x. So that means the volume of this cylindrical shell is 2 pi rh times dx. Now, if we want to use this technique to find the volume of our entire solid of revolution, that means we're going to use an integral to add up the volume of each of our little cylindrical shells. And that's going to give us volume equals, and I just took this 2 pi from my volume formula and pulled it out front because it's a constant. So our volume is going to be 2 pi times the integral, which represents a sum of our radius times our height, so radius of this cylindrical shell times our height, both as functions of x, dx. And we'll add these up from our x values where we're starting, x equal a, to where we're stopping, x equal b. Let's see how this works by doing an example. So let's just dive in and do an example and see if we can make sense of this. Find the volume of the solid formed by revolving the region bounded by y equals 0, x equal 1, x equal 3, and y equals x cubed plus x squared plus 1 about the y-axis. All right, so here's my y-axis and my x-axis. We're bounded by y equals 0, that's the x-axis, x equal 1, x equal 3, and then this polynomial. And I wasn't quite sure how to draw this polynomial, so what I decided to do to help me with my picture is I took x equal 1 and I just plugged that in so I could get a point. When I plugged in 1, I got y equal 3, so I just kind of drew, this is supposed to represent the point 1, 3. And then when x is 3, if I plug that into my polynomial, I ended up getting y equals 37. And so I drew that up there. I don't know the exact shape, but this picture should be good enough to help me get my problem set up. So we're taking this region that I have drawn, and we're going to rotate it around the y-axis. So we're taking this region and we're rotating it around the y-axis. And so what we're going to do is we're going to try to use the shell method to find the volume. The reason we want to use the shell method is because it would be really nice to work in terms of x. This polynomial, y equals x cubed plus x squared plus 1, I don't know how to solve that for x. It's solved for y. So I'd really like to work in terms of x. That means when I create my little rectangles, the width of each rectangle has to be a delta x or a dx. So the rectangles that I draw when I slice this object up have to be vertical so that they have a little width of dx. If my rectangles are vertical, that means they are parallel to my axis of rotation. And so when I rotate these rectangles around the y-axis, the shape that I'm going to get is actually a cylindrical shell. I'm not going to get that disc or washer because my slices are parallel to that axis of rotation. So I'm going to try to use my volume formula for cylindrical shells. I'm going to have to integrate 2 pi times the radius of my shell times the height, both as functions of x, dx. All right, so the radius is going to be the distance from the axis of rotation to wherever you are on this object. Our axis of rotation is the y-axis. That's x equals 0. And then we're going to come out to some unknown x value. We'll start at x equal 1 and we'll stop at x equal 3, but our radius is always going to be equal to whatever our x value is. It's this distance I have drawn in red, which represents our x-coordinate or our x value. The height of our cylinder, I've tried to draw that in yellow. The height of our cylinder is given by the y value on this polynomial. And the y value on this polynomial is x cubed plus x squared plus 1. So that would be the height of our cylinders. Plugging that into my formula, my volume should be 2 pi times the integral of x times x cubed plus x squared plus 1 dx. And my bounds of integration are going to be x values as well. We are starting at x equal 1. That's where this object starts. And we are stopping at x equal 3. So my bounds go from 1 to 3. All right, let's see if we can solve this. I would distribute the x first, and then I'll be able to integrate. The 2 pi is a constant, so it stays there. Antiderivative of x to the 4th is x to the 5th over 5, plus antiderivative of x to the 3rd, which is x to the 4th over 4, plus antiderivative of x, which is x squared over 2. And then I'll plug in my bounds of integration. I have to plug in 3 for all the x's. Then I have to plug in 1 for all the x's and subtract those values. I used my calculator to finish this, and I got an answer of 724 pi divided by 5. Let's set up another one. Find the volume of the solid formed when the region bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equal 1 is rotated about the y-axis. And then we'll try it rotated about the line y equals 3. But let's just focus on part A. So y equals x squared plus 1, that is a parabola. It's been shifted up 1 unit. y equals 0 and x equals 0 are my axes, and then I've drawn in x equal 1. So the region we're talking about lies under the function y equals x squared plus 1 and lies in the first quadrant. We're going to take this region and we're going to rotate it around the y-axis. To use the shell method, I'm going to make my slices, my rectangles, parallel to that axis of rotation. So vertical slices would be parallel to the y-axis, parallel to the axis of rotation. Using vertical slices means my width of each little rectangle is actually a dx or a delta x. And I really do want to work in this order. If I were to make my slices horizontally, part of this object would have cross sections that are circles or discs, and the other part would be washers. So I'd actually have to set up two integrals and find the volume of the two different parts of the object separately and then add them together. But with the shell method, we only have to set up one integral. So I'm going to make my slices vertical, parallel to my axis of rotation, so my width is dx. The radius of my cylindrical shells, so again, we're taking this blue rectangle, we are rotating it around the y-axis to create a cylinder. And the radius of that cylinder is the distance from the axis of rotation to wherever you drew that rectangle. That's your x-coordinate. So the radius is determined by my x value. Where am I in this object? So radius is my x value. The height of these cylinders is determined by the y value of this parabola. That's the top of my rectangle. My parabola is y equals x squared plus 1, so my height is going to be x squared plus 1. Using the shell method, I'm going to have to integrate 2 pi x times x squared plus 1. And my bounds of integration are going to correspond with the x values that this region spans. So we're starting at x equals 0, and we're stopping at x equal 1. So my bounds of integration are 0 to 1. To integrate, I'll start by just distributing that x. So the thing I have to integrate is actually x cubed plus x. So 2 pi stays there, that's a constant, and we'll get x to the 4th over 4 plus x squared over 2. Plug in my bounds of integration, so I'll plug in 1 for x, then I'll plug in 0 for x, and subtract the values. And I ended up getting 3 pi over 2 as my final answer for my volume. All right, what if I rotate about a different line? So let's consider this exact same region. So same picture for our region, but instead of rotating about the y-axis, I am going to rotate over the line x equal 3. So I'm taking my region, rotating it over the line x equal 3. We're still going to create our vertical slices to use the shell method. When we use the shell method, our slices are always parallel to that axis of rotation. So if I take my vertical slice and I rotate it about the line x equal 3, I get my cylindrical shell. The width of my cylindrical shell is a dx, so once again, I'm still working in terms of x. The radius of that cylindrical shell is going to be the distance from the axis of rotation to wherever I drew my rectangle, wherever I am in the object. So I've tried to draw that radius in purple on the screen. I'm highlighting it right now. So radius is this distance that I'm highlighting. We're trying to find a horizontal distance, so we can take the right side minus the left. This line segment I have drawn starts at x equal 3. And it's going to stop wherever I draw my rectangle, at whatever x value I am at in this object. So my radius is actually going to be 3 minus x. Okay, so the distance of the purple line is 3 units minus whatever x value you are at. I always like to think of horizontal distance as taking the right side of the line segment minus the left side of the line segment. The height of my rectangle is the same as it was before. It's still given by the y value of the parabola, which is x squared plus 1. So what we're going to be integrating is 2 pi times our radius times our height. So 2 pi times 3 minus x times x squared minus 1. And the bounds of integration always correspond to that region, the region I have shaded in, the region that you're drawing your rectangles in, that you rotated to create your object. So our region starts at x equals 0, stops at x equals 1. To do this integral, I would FOIL out the 3 minus x times x squared plus 1. When I did that, I got 3x squared. That was first. Outer plus 3. Inner minus x to the third. Last minus x. And that's something I can integrate. That 2 pi constant stays there. Antiderivative of 3x squared is x cubed. Antiderivative of 3 is 3x. Antiderivative of x to the third is x to the fourth over 4. And antiderivative of x is x squared over 2. So I'm going to take my bounds of integration, plug them into this antiderivative. So again, my antiderivative is 2 pi x to the third plus 3x minus x to the fourth over 4 minus x squared over 2. I plug 1 in for x, I plug in 0 for x, and subtract them. And I ended up getting 13 pi divided by 2 as the volume of this object. Now you can use the shell method by making horizontal slices. If your axis of rotation is horizontal, let's say you're rotating over the x-axis, you have a horizontal axis of rotation, you can use horizontal slices, which means you would be working in terms of y. So you can do the shell method sideways, working in terms of y. It's still the same formula. You're still taking your radius times your height times 2 pi, and that's the thing you're integrating. I'll make sure to have some examples listed in the other resources. But if you have any questions, please reach out. I am going to stop the video here, so let me know if anything in this video is unclear.